to see you, and thank you all for being here and for the organizers for asking me to speak about this today. So I decided to call this talk the recent observational advances in our understanding of interior transporting stars. And I would like to highlight that if we look at the mass range here, we have a very large mass range. And I'm an expert in massive star evolution, so I'm going to stick to the massive star N today, unfortunately. Well, I think that that's a really cool part of the mass range, so it's not going to be that bad after all. And we also have some really good experts in the low mass N, for example, our chair, and in the panel later today, so we can talk more about the low mass stellar evolution then. But today we're going to, in this talk, I will focus on the massive stellar evolution. I should also mention that I'm not really a full-feathered observer. My background is in evolutionary modeling, binary evolutionary modeling, spectral modeling, population synthesis modeling. But I have done some observations recently that are based on the background picture here. So what you can see is a UV map of the Large Magellanic Cloud there, and we're going to go back to this later in the talk. I wanted to put it as a starting slide for you to remind yourself how important UV is and how great it's going to be if we start to build more UV telescopes. Okay, so what is really interior transport? You know, it took me some time to sort this out in my brain. What is transported in stars? Like, what is it really? So we can have, for example, angular momentum. So that is affecting the spins of stars, the mass loss of stars, mass accretion efficiency if you have binary interaction, pulsations, etc. Also, chemical elements can be transported inside of stars. This is usually called mixing. So you think things like convection or thermohaline mixing, etc. This affects the lifetime of the star. If you provide more fuel to the fusion, you can change the lifetime. Also, the density structure, the surface composition, the core size, things like that. You have energy transport in the star. So if, for example, energy is transported efficiently, you have a smaller star. If it's less efficient, it's a larger star. This can change when binary interaction occurs, really kind of important. And mass loss, the color of the star. And I know that the last one doesn't really belong here, so magnetic field is maybe not transported, but when you think about things happening inside of the star, magnetic fields are affected. So just because I got a little bit into magnetic fields during this workshop, I decided to include magnetic fields. Okay, so what affects this? I would have wanted, you know, a nice arrow to a few things. This doesn't really work because everything seems to be dependent on each other. So for example, for the angular momentum, so we can have tides, maybe mass loss, and for chemical mixing, maybe convection, and magnetic field can affect the angular momentum, but we have magnetic fields here. So this is a little bit messy, and it's something that is kind of good to keep in mind if you're, for example, doing evolutionary modeling, that everything is dependent on each other. So it can be good to remind yourself sometimes that, okay, if I neglected magnetic fields, what happened then to, for example, the angular momentum transport? When it comes to the transporting stars, this is a fun topic because I think it depends, it affects many parts, right? So let's see. Yeah, for example, the structure of the star is affected by transporting. So we will change what kind of supernovae and transients that are produced. The spin of the object and the angular momentum transport affects what the gravitational waves look like. You can have differences in the magnetic fields of contact remnants, so there's really strong magnetic fields, for example. And if you have efficient mixing inside of the star becomes smaller, hotter, emits more ionizing radiation, changes how galaxies look like. And that ionizing radiation can really boost cosmic ionization, for example. So and this last one is the hardest to describe. So this is, for example, I didn't even find a beautiful picture. So this is things like, for example, if you have a hotter star, maybe it will have stronger wind mass loss, or if you change the structure so that you get a different supernova, you will have a different mechanical feedback and different chemical yields depending on how well mixed the star is. So I will go a little bit in different topics today, and not everything, but I will start with a little bit on convection and convective penetration, then go to rotation, both like the rotation ray and the rotational mixing. And then I will go into a little bit on magnetic fields and our understanding of magnetic field evolution, maybe we can call it. And then I have a part about binaries, of course, because why not? So let's start with the extent of the main sequence, which is what has been used to constrain how much convective overshoot or convective boundary mixing or convective penetration, whatever we would like to call this thing, can be constrained. So this work has been done much by Norberto Castro, who has been looking at here, so in color shading, no, in the gray shading, that's actually a sample of massive stars in the galaxy. And he compares here to the models from the Geneva Code, and that's what is shown in triangles. So these are tracks of different evolutionary models. So this is not the luminosity, really is a slightly different thing, but sort of. Okay, and so what we can see the zero age mean sequence of the stars, it's sort of there, so it seems quite okay. But the terminal age mean sequence is there, yeah? Right, so this is just from the density of stars. Where are stars located here? And it seems like there is this extra region that extends a little bit further, and it's larger the more massive star you have, and the smaller the less massive star you have. So this was in comparison to the Geneva models. You can also compare to, here are some bone models, which have a constant overshoot, just a little bit larger. So you can see that there is now a difference in the slope, and it seems like this is a mass-dependent process. So that is stuff that Norberto has been doing. Here is the sample from 2014, which is in the galaxy. It's less evident in the large and small Magellanic clouds. I would say that this is clearest when you look at the galactic sample. But he is continuing, and you can see the most up-to-date version is in 2021. So when talking about the HR diagram and the extent in the HR diagram, I want to mention one thing that is possibly related, but it is really interesting and ongoing in the massive star community. And so this is work by Gonzalo Olgado from last year. So here we have also a galactic sample of massive stars located here in the similar, or actually exactly the same diagram, compared to Geneva models. So what we can see is that there is a dearth of massive stars here. Okay, so this is weird because the massive stars, they spend most of the time early during the main sequence here, and less time there. So it's slowest in the beginning. And so we should have more stars located close to there, if indeed stars are born on the zero age mean sequence. So that's what has been discussed. Are stars really born there, or do they never really reach there, or are they enshrouded with material, or is there something else going on? So I also want to mention that similar work has been done in the SNC by Abel Schottemeyer, and it is very similar results. So this is interesting and fun, and could be doing with mixing or something like this. So let's leave the convection and go to rotation. So first, let's talk about rotational mixing. So what is rotational mixing? Let's see, you have a star here, burning hydrogen in the center, and some receding core. And it's rotating, so you have, because of centrifugal force, a little bit larger radius in the equator, therefore lower temperature on the equator than on the pole. So this drives a flow. It is called meridional flow. It goes from the pole down and then in and up. Yeah, so this is a large-scale flow that is supposed to mix the star. So if we look here at the structure of such a star during main sequence, you have this convective core with a hydrogen burning in the center, and a little bit of nitrogen coming out there from the CNO process. The meridional circulations, or Eddington-Sweet circulations, that comes from the authors who wrote those functions, I think, yeah. It's acting here in the envelope. It doesn't really reach into that gradient. So this is supposed to be really efficient there. And there's models maybe where it can reach into the gradient, but I have not seen sometimes. So what you may rely on is shear. So this is just because I draw the star rotating like this, the shear is going to be towards you, yeah, and acting in that region. So the shear is acting here. And so you rely on the shear and the meridional circulations to bring out this helium and nitrogen-rich material to the surface and hydrogen-rich material to the core. So this is the rotational mixing. And when this acts, you increase the helium abundance in the atmosphere and decrease it in the core. Right, so you become slightly more helium-rich there, and you can bring out nitrogen to the surface, which is really the key chemical element that people have been looking for to try to identify whether this is happening. Okay, so what you do then to try to check whether this works, this is called a Hunter diagram. It was created by Hunter in 2009. B-type stars, and you can see as a function of rotational velocity on the x-axis and nitrogen abundance on the y-axis. So you should have, with higher rotation rate, higher nitrogen abundance, because with higher rotation you get more nitrogen to the surface. We have a similar diagram for O-type stars made by Nathan Green. That's 2017. Sorry. And you can see that these stars are located in the diagram. There's much upper limits. It's hard, fast rotation, broad lines, weak nitrogen. Something to notice is that we have this slowly spinning nitrogen-rich stars. What does it mean? We don't really know, but I think something that has been interesting to see is the work by Kavli on magnetic braking. So if indeed we have magnetic fields inside of stars, they can break the spin right in time for nitrogen to be encouraged up to the surface, but then the star spins down. There has been other ideas. So for this slide, I want to thank Falk, because I went through the work of Conning Ertz from 2014, where they look at a galactic sample of B-type stars and make, again, the Hunter diagram here. And you can see that's not clear. No, you don't have really a clear trend going on here. It is hard because sometimes stars are formed with more or less nitrogens, could be to do with that. But something that they did find here, so look at the black markers, because that's data, and the blue are models. So what they found was a trend in nitrogen abundance on the surface with the frequency of the dominating acoustic mode. So with a higher frequency of that dominating acoustic mode, you have a higher nitrogen abundance. And the same with temperature, higher temperature, higher nitrogen abundance. So this temperature is reversed. It always happens with temperature. So that's interesting. I wouldn't take a side here. Say that it's interesting. Okay, so then what happens if rotational mixing becomes more extreme? So then you manage to mix the envelope and the core so that they have equal composition gradients. So this, it's not gradient, it's equal composition throughout the star. Chemically homogeneous is what it's called. So when that happens and the star continues fusing, eventually you are going to create a helium star. There's only helium throughout the star. This is quite an extreme scenario. If this really works, then this is going to change many things. So for example, this is a diagram showing you the emission rate of hydrogen ionizing photons on the y-axis as a function of time for a stellar population, so a star burst. This is made by the BPAS model. And so what you can see here, so let's note this is log scale. So this is very big differences. And so most massive stars, they die quickly after just a few million years here. So it's really like, this is a sharp drop. And so what they did, they invoke chemically homogeneous evolution for low metallicities of stars that accrete material. And that gives rise to this bump. And this bump, you're like, oh, that doesn't look super much. This is huge. This is really huge. So what that does is it boosts the ionizing emission so much that you create a cosmic reionization in simple models at redshift 9. It's a lot. So if this exists, you know, these stars are really, really interesting. We should find them. How do they look like? Okay, again, more theoretical work. Sorry about that, but it's interesting. Yeah. So Brangitsa Kubatova, she made these models, spectral models for how these stars may look like. For most of the time, they look like this. Okay. So if you're not familiar with looking at spectra, this looks very much like O-type stars. They have similar brightness as O-type stars. Maybe they are a bit hotter than O-type stars, but they have very similar spectra. It's only in the very last stages they start to look like ultra-J stars when they have helium-rich surfaces, like pure helium surfaces. So this can be really, really hard to identify, but could be really crucial for understanding how stellar populations evolve. Yeah. So I think that one of the most interesting recent tests that have been done was made by Michael Abdul-Masih, where he looked at overcontact binaries. So what is an overcontact binary? You have binary star here, the Roche potential, and one star starts to swell up as it evolves, and it starts to interact with the other star, but the other star is so nearby, so it also swells up, and they start to create this kind of peanut shape. Okay, so just because I draw this from above, let's like turn it and put, yeah, so let's look at it from the side. So you have this really fast rotation, and they are tidally locked to each other. So you should, just from the the really short orbital period, should have really fast rotation rates and therefore invoke these meridional circulations and rotational mixing and things like that, slowly turning these stars into helium balls that could collapse to black holes and create gravitational wave events also. Let's throw it out there. Yeah, so that's an interesting theory as well. So it could be fun to, not only for rotational mixing to find this, but also for the gravitational waves. So this is a model that Michael did for one of those overcontact binaries. It's a massive overcontact binary, about 26 plus 19 solar masses. And you can see this really surely, certainly, because this is a touching binary. And so because you can see both components in the star, you can determine what's the masses dynamically. So this is pretty clear. When he modeled these stars, so he did a very careful job. He actually made a spectrum for each of the little triangles, if you would look closely there, and to figure out what's the temperature and luminosity of these stars. They end up in somewhat weird positions in the HR diagram. So let's note here, so that as the solid point, I think it's the primary, the 26 solar mass star. And the rotation rate is about 300. So from single stellar rotating models should evolve something like that. Huh? It doesn't really look like that. It's a little bit hotter, a little bit more luminous, and it's extra extreme for the companion star, the 19 solar mass star. That should be done here. So something here is making the temperature and the luminosity brighter, hotter than what the single stellar evolution tracks show. Now, this is not a single star, so there is a lot of things we can think about, but I think this emphasizes that there is things that we're missing still a little bit. And something too, when you look at the surface composition, it is not enriched. Here, the colored bands, that's where the composition of nitrogen was measured. And the lines show you the models. So they are really below the lines, which indicates that this is not a nitrogen-rich surface. And if you look at carbon and oxygen, those should be under abundant, and they are not. So what does that mean? Does it mean that we didn't dig into the CNO processed material? Or does it mean that this is working in some such slightly different way? So I think there are some things that we can still understand here. So some mechanism, increases the effective temperature and volumetric luminosity, but nothing is happening really to the surface composition. Questioning, I would say, what's up with rotational mixing. So let's look just at the rotation rates now then. So what do we know? This is measurements by Oscar Ramirez Agudelo back in 2013-15 of O-type stars in the Large Magellanic Cloud. And you can see that they reach really high surface rotation rates, hundreds of kilometers per second. So this is really, really fast rotating stars, and the peak is at 100. So it's a lot. Okay, so if we now think about what does it mean, where does that leave us, what other data points we have. So if we just like extrapolate to the black holes, because this supposedly could be progenitors of black holes. This is a new plot from the LIGO data in O3b, where you can see the black hole spins. We think that from that data, the black hole spins are consistent with low black hole spins. Okay, so you're like, yeah, but maybe you know that star is rigidly rotating. Maybe it is connecting so that the core is also slowly rotating. Well, yeah, we don't know. But then let me show you a contradictory thing, maybe. So here is, I thought that this graphic was very nice from Maya Fishback, where you can see the spin parameter in a cumulative plot. This is for the gravitational wave black holes. And this is for black holes in X-ray binaries. So we have slowly spinning black holes in gravitational wave binaries and fast spinning black holes in X-ray binaries. And I should note that in the case of high mass X-ray binaries, when you have a massive star feeding the black hole, there is not enough time to spin up that black hole. So this doesn't happen from accretion. There is something else. So does it mean that they have different evolutionary backgrounds? I mean, the gravitational wave black holes, they are like a small fraction, tiny fraction of the massive stars, right? So do they come from some special part of the parameter space or so? I would say we still have a lot of things to resolve here. It would be great to understand what's going on here in the dash tree. Yeah. So, and something else to understand is like, yeah, how the stars really rotate. Is it rigid rotation, so efficient angular momentum transport? Is there some faster, some split in between, some core and envelope rotation rate? Something else here, okay, I made up some different things here. So we can have like, you know, smooth differential rotation, some accretion, fun. Or here, like in the convective region, we have differential rotation there. Fun things. But I'm going to leave this to Mai, because I think that Mai will do a very good job at talking about rotation rates of massive stars tomorrow in science. She's done much more than me. So we think that the rotation and the interior rotation can be connected to magnetic fields. So what do we really know about the magnetic fields and how the magnetic fields are inside of stars? There has been a recent effort in measuring magnetic fields on massive stars, primarily from the MINES, Bob, and Bynamics surveys. And I'm going to show you a bit from MINES. So what do you do? So let's see here. Yeah. So this is how you can identify that the star has a magnetic surface. So what you see, you take a spectral line, and you use a spectropolarimeter. So you split the light into the different polarizations, and you can see the characteristic shape here in the Stokes-V part of that line. And so this star had a magnetic field of about 100 Gauss. So it's not super magnetic. And so for the O stars in the MINES survey, they were around 100. They found 7% are magnetic. Among these, the magnetic field is not very strong, 100 to 1000 Gauss. And the uncertainties maybe 50 Gauss or so. So the surface magnetic field can be magnetized, but not like hyper strong. How does it look like? So here are some examples. So let's start to look at the simple one here. So this is an early B-type star, and you can see that it has some complicated magnetic field topology. And this it's giving you a better picture, I would say. So this is telescope. It's a early B or late O. I never remember. But it shows you 3 models. So for model A, that's the top row, then B, and then C, and then it's just a viewing angle. And so this was just to emphasize that this is model dependent. So it can look like that, or like this, or like that, you know. So it's still things that we need to resolve, but it seems like this is complicated, the magnetic field morphology. And it's interesting then to talk about the magnetic fields in neutron stars, because I think that the NICER survey did a really good job recently in actually mapping out how does the magnetic field topology look like. So here is data from NICER. The top here is the data. So you can see energy of a pulsar. Now we're looking at pulsar here, and as a function of phase. And so when the hot spot is coming into view, you can see more. And then there is a model. So you make a model that matches the best. So they cover large ranges of how does the spots look like, and what does that give rise to, and which is the best fit model. So they did try, and even though I would say probably the spots were not completely excluded, by far the best fit model did not favor to dipolar spots. So this is the best fit model for that pulsar. So you can see it has a spot. Here it is a spot, and the crescent. Okay, and they are not opposed to each other. They are on one hemisphere, and we see it in this angle. So that's kind of fun, because it would mean that we need to revise this picture a little bit, probably. And it probably looks more like that. So, I mean, when I saw this, I was like, oh, this is fun, because it looks, in some sense, it's kind of similar to that massive star. So the question, is there a connection between the magnetic field topology of massive stars and the neutron star, or is it just created during the supernova, this topology? What really happens? Then, let's see, just want to keep track of time. Okay, great. Then I wanted to also show you some stuff on the magnetic white dwarfs, and this is work by Ylva. And so to summarize, white dwarfs, about 20% of them are magnetic. Magnetic fields are much stronger than massive stars, kilogauss to gigagauss. And so there is several evolutionary scenarios for how to create a magnetic white dwarf. You can either have a magnetized stars, it was magnetized throughout, and you get a magnetized white dwarf. Or you had some magnetic field on the inside, and that got exposed when you created the white dwarf. Or you merge 2 white dwarfs, and then in the merger process, you create that magnetic field. So Ylva, she found 3 massive white dwarfs that are magnetized in young clusters. This is fun. So these are 3 spectra. Let's show you here. And the H alpha of this star, you can see the Zeeman splitting. This is magnetized. We could find megagauss-ish magnetic fields. Okay, so just because this cluster is young, we can exclude that these magnetic fields were created by gravitational wave mergers of white dwarfs. Okay, so it could suggest that the white dwarf was created with a magnetic field as it died. Also, the magnetic white dwarfs, that was 20%, right? It's more common than how magnetized stars are in general. So does that mean, then, that this is an exposed magnetic field? It could suggest that. There was another really nice white dwarf, but I just have to throw that out there because this is a binary, probably. So it looks like that, and you're like, yeah, okay, maybe if you're familiar with spectra, that's H alpha. But what's the other lines? They are also H alpha. Yes. So here, if you plot as function of the magnetic field, H alpha is doing crazy stuff when you go up in hundreds of megagauss. Yeah, so this is really strong magnetic field range. And so what happened from that methodology, she also has shorter wavelength spectra. You can see that this magnetic white dwarf has a really, really strong magnetic field of about 800 megagauss. It's also really fast spinning, and this matches quite well with the merger scenario. So it could be that this is a merger product. So now, wouldn't it be great if we could find some point in between here, understanding what's the interior rate of rotation with time? Also, maybe if we could look inside some stars to confirm this. And I think we can do this if we look at binary products, envelope stripped stars. Okay, so what is that? If you have two stars in a binary, the most massive star evolved first, stripped of its hydrogen-rich envelope to expose that helium-rich core. In the HR diagram, it looks like this. Here we have a single star evolving to the red, exploding as a hydrogen-rich supernova. If you strip the star, the line changes direction, and it's a hydrogen-poor supernova in the end. And the stripped star spends most of its life over there, the really hot part of the HR diagram. If you're wondering, the color is flux, ionizing flux. So it's also really interesting. You remind yourself of the chemically homogeneous evolution. Just to have an idea how deep we go, this is the structure. As you strip the star, you end up with something like that. So you should have a nitrogen-enriched surface and helium-enriched surface. It may also burn helium in the core. So basically, this is how the picture looks like. If we also throw up a Kippenhahn diagram, this is the main sequence. Here you have the mass transfer phase. That's the long-lived stripped star phase. So you can have this hydrogen-burning shell there. You can see this is really what used to be the main sequence core. So here the green is convection and the purple is overshoot. And then that's late evolution when you become supernova. So these stars probably exist. About a third of all core collapse supernovae are stripped supernovae. And they also constitute some important part here in the evolutionary channel to the binary neutron star merger, for example. We have two, one here, one here. This phase is fun. Here. Yeah. Because you can emit gravitational waves and have tidal interaction. Yeah, very fun. Let me just double check. Okay, great. So just to summarize, how do the stripped stars look like? So they are hot stars, 30 to 100,000 Kelvin. Small, less than a solar radii typically. Can cover a range of luminosity, up to millions of luminosity, solar luminosities. Hydrogen-rich and helium-poor, nitrogen-rich as well. So what is that? Some people may say Wolf-Rayet star, others subdwarf. Nothing is wrong of those. None of those are wrong. If you look at the mass range of helium stars, in the low mass end you have the subdwarfs, and the high mass end you have the Wolf-Rayet stars. There is a large range that has not really been observed. In between there, we have the progenitors of merging neutron stars, stripped envelope supernovae, not been found. So that's where I have done work recently. This is a survey with Maria Drought and Bethany Ludwig from University of Toronto. We have more people accreting here. So I have two students, undergraduate students, Beryl Hovis-Afflerbach and Ashley Carpenter, working with me in this survey as well. And that's where this picture come in. Okay. So I can notice that the sign is coming up, so let me move forward. Oh, maybe, okay. So how do you find these stripped stars? So this is a model of a spectral energy distribution for a 4 solar mass stripped star. The wavelength on the x-axis and flux on the y-axis. And I labeled here, so here is optical range, ultraviolet, ionizing regime. Much ionizing photons, it's a really hot star. So even though most of it comes out in the ionizing regime, there is still stuff in the optical. So maybe you can see, maybe we can still see this star. But it usually has a companion here. So if you just look in the optical regime, it can be really, really hard to identify what is a stripped star. It even has the same slope of the yeah, so the color should be the same. But what you can do, you can compare it to the UV. So here is the first step, why UV is so important. So if you measure the color of the star and the luminosity, you may be able to identify that this has UV excess. So what we used photometry from the SWIFT satellite, the UV satellite. No, actually X-ray, they just happen to have a UV part. And optical photometry from the ground. And so if you look at, this is sort of an HR diagram. It's called color magnitude diagram. Survey thingy. Brightness on the y-axis and color on the x-axis, with blue here, red there. Strip stars should be blue wards of the 0H main sequence. The data looks like this: large and small Magellanic Cloud. Here is the 0H main sequence. That's some Wolf-Rayet stars. That's where we expect single strip stars. So if they were single, they are not. And this is stars that we follow up with in the survey. So these, I think, we can claim are actual strip stars. So we did that by following up with spectroscopy from Magellan telescope, optical spectroscopy. We found 3 main types of stars. You can see on the top and the middle, they have lines of ionized helium, so that's a sign of really high temperature. And in the middle and bottom, you can see lines of hydrogen that are really strong. So those are signs of B-type star. So probably what we are seeing here is 3 types of stars. On the top, where the strip star is dominating the spectrum. In the middle, where you have contribution from both the strip star and its companion. And in the bottom, where the companion star is dominating most of that. So I'm going to skip the part. You can look briefly at the spectra. This is how the spectra look like for the stars that have the ionizing, where the strip star is dominating the flux. And so what you can see is that there is nitrogen lines. Check this nitrogen-rich surface, that we expected that. There's absorption lines, so that means that you can measure properties of the surface of the star, which means you can see things that used to be the core of the star. There's no emission lines, though, from the wind, so we need to go to the ultraviolet to measure wind mass loss. This is going to be important for how the star evolves, whether it interacts again, what type of supernova it is. So in the end, after doing some analysis of this survey, which is coming out soon, we found that these stars are really hot, typically above 70,000 Kelvin. They are helium-rich on the surface, so this is mass fraction, 70–90% of helium. Really dense, so typically main sequence stars have like four maximum, log G, 4. This is 5.5. And when you put them in the HR diagram, they overlap nicely with 2 to 8 solar mass strip stars. It typically corresponds to about 8 to 20 solar mass progenitor stars. And this is just the beginning of this survey. So I think that you can do a lot of things with this. For example, measure what's the rotation rate to understand better how the core rotates, or investigate what's the magnetic field like, or from the photometry, maybe check what's the mass distribution of these objects to get an idea of the core overshoot. And so we have some projects going on there, which I think is fun. So let's put this together in a summary. So I had a few things that I wanted to convey. So I think the extent of the convective core, so the convective boundary mixing is mass dependent. There seems to be some extra mixing or transport needed to explain the high luminosity and temperatures in overcontact binaries, but it's not really clear whether chemical mixing is actually efficient. So stars likely have magnetic interiors. We saw this from the white dwarfs, but the topology could be quite complicated and would probably need to investigate a little bit more. And the strip stars, maybe they can be an opportunity to look into the interiors of massive stars at evolved stages. So with the last slide, If we look at the wavelength range here, so I cut the gamma rays, I'm sorry about that. It goes from X-rays to radio. What do we have? Huh? So stars, they shine in this regime. If you're interested also in like neutron stars, you can go there and there. Yeah. But the stars, when they are alive, they're there. Hot stars, more high energy photons. Cooler stars, less energy photons. And where do we have instruments? So this is a subset, right? So I'm definitely not covering all, but we have much in the visible and infrared. It's been really popular lately, like Roma, JWST. I mean, that's great. Yeah, this is very nice. Lots of stuff. For example, if you want to see distant universe or so, very nice, because then you redshift hot things into that regime. But if you want to see individual stars, I think we can really easily argue it would be great to have stuff here. Huh? So we have a problem. So the ionizing photons, we cannot get them because there is too much neutral hydrogen surrounding the Earth. So that's not going to work. But at least maybe we can make an effort here. I think it would be great because it's really crucial for measuring the wind mass loss rates of massive stars or in general stars. Seeing strip stars, you can do that with the UV. Swift has a photometer and it's still alive, but it's not a spectrograph. HST is old, as you know. Soon we have nothing. So there has been great effort with the Ulysses survey of collecting spectra of massive stars in the ultraviolet and actually doing careful work here. And I should mention also with the X-shoot-U combination is going to be a really powerful library of massive stellar spectra. I will not say that it's enough. I don't think it's enough. I think we need more. So it would be great to have even more ideas of the instruments in the ultraviolet. And I was happy to see that in the decadal survey, they recommend UV instruments to happen in the future. So that I look forward to. So with that, that was all that I had to say now. So if you have any questions, I'd be happy to take them.
Any questions?
Yes. Hello. Hi. My name is Vicky Adachi. Thank you for a very nice talk. I was wondering, you showed the picture of the nitrogen abundances as a figure. Nitrogen abundances as a function of V sin I with excess in the lower range of the V sin I values. So maybe you mentioned I missed it, but how do you know you don't see the stars fall on?
Yes.
And they're actually rapid rotators. Because that's not really a measurement of the rotation rate.
It is true. So yes, this could be happening, right? But this is many stars in comparison to the sample. It is too many stars to be able to argue that those are all pole-on seen stars. So too large fraction.
So each dot is basically a measurement of a star.
Each dot is a measurement of a star.
Doesn't feel that many.
Well, it's like more than 10%.
Yeah, but I mean, you can have up to 20%. You still have rapid rotation, and they would fit into your group number one, no?
Would they?
I think so. Yeah, I'm naive.
I think that it's pretty. So my impression, I didn't do this work myself, but my impression was that this is pretty robust. That these are indeed at least a subset of them. Robustly measured, high nitrogen abundance, and slow rotation rate. But yeah, it's good. Yeah.
So this is Evan Anders. Thanks for the nice talk, Ylva. I have a kind of naive question. So you mentioned that in the MIME survey, only like 7% of the stars were measurably magnetic. and then only like 20% of white dwarfs. So does that just mean that basically, does that mean those stars don't have like a large-scale global magnetic field, and maybe hydro's an okay approximation for them, or does that just mean it's hard to measure the fields there?
Good question. So let's see. We were here. So you can measure probably magnetic fields down to 100-ish Gauss. So it could be that the other stars have a lower magnetic field strength. Or maybe it was harder because some errors are larger than that. It depends on the star. So it's, I think that it's from the survey, it's pretty clear that a large fraction of massive stars don't have strong magnetic fields on the surface. There could be things inside. People have argued that this is a result of mergers, massive stellar mergers that invoke this magnetic field. I wanted to mention this during the talk, but Jason Grunhat has recently published a paper on Friday or something, so I didn't have time to read it. But it was very nice because that's actually a binary with a helium-rich star that is magnetized. So that could be like donor that become magnetized or something like that. But it's something I would need to look closer into. So it doesn't necessarily have to be, I would say, merger products. Now, maybe I didn't hear the entire question, Evan. Did you ask him something more?
I think that was pretty much it. I was just wondering, so you say there's 50 or 100 Gauss of uncertainty, and like, I guess is like, if the magnetic field is smaller than that, is it super important at the surface at like a 5 Gauss level, and we still have to worry about it, or not super much?
Yeah, so if it's important, I mean, I guess it can still do things, but I mean, it depends on how it looks like on the interior of the star too. Like how does it grow when you go inside? There is models of Jolt-Castelli where you can see how the magnetic field strength increases even just in the envelope if you make a certain model. So yeah, I would say the surface is maybe. The surface is what you can measure, but maybe it's not the most important part of the star, so for that. Yeah.
Hi, Ylva, it's Dominic. Thanks for the great talk. Excellent as always. Just to pick up on this a little bit, so it's a pretty robust result, but most of these stars have been modeled with a predominantly dipolar geometry for the magnetic field. And so that paper from Sam that came on the archive a couple of days ago is actually for Plaskett star, and it's showing that actually there's a non-negligible contribution from the quadrupolar and higher order components to the field, and that can sometimes suppress the polar field strength of the dipole, and therefore you might be missing the magnetic field. So it's a really interesting interplay between the different components of the magnetic field, which can potentially hide magnetic stars. But yeah, what you've said is a nice overview, I think. I have one thing, if I can keep going. Is that right? Thanks. Without taking a side, I'm going to say something controversial. What if the overshoot is not mass dependent, and we're just measuring something that seems to look like overshooting is mass dependent?
Okay, you have to. Can you specify a little bit? What do you mean with that?
So there's a lot of people in the binary community right now that are arguing, and I have no real opinion on this that I want to share right now, but whether overshooting is a mass-dependent quantity. So with binary stars, you get a dynamical mass, so it's completely model independent, and then you can compare your dynamical mass to your evolutionary mass, and you find sometimes it agrees, sometimes it doesn't. But I would perhaps rephrase this a little bit to say mixing is mass-dependent. Because one of the things you can play with is the core boundary mixing. The other thing you can play with is the envelope mixing. And you very nicely gave the overview of Michael's work on the overcontact systems, and he shows that it's also the envelope mixing that is underestimated in the models, and that will also give you a width to the terminal edge main sequence if you increase the envelope mixing as well as the overshooting.
Yeah, it would, right? Yeah. Something else that is interesting when you look at these diagrams is whether these stars, in fact, are not main sequence stars, but maybe they are evolved blue supergiants that just never evolved further. there is still, it's primarily something happening in low metallicity environment, but I think it can be interesting to consider, like, did you really catch the terminal age main sequence with that line? And as you say, is it uniform, or does it matter whether it's a binary, there's extra mixing in some stars, less in others? So yeah, it's definitely still, I would say, something worth more work.
Yeah, very nice talk, Ylva. Just on this plot, a word of caution on this. This is a very biased sample. This is a literature study, and there seems to be a gap between the O and the B supergiants. We don't see that gap in the flames data in the Large Magellanic Cloud, and therefore perhaps the overshooting is even larger. So I'm a bit concerned because some people will have studied O stars, and other people will have studied B stars, and you introduce biases that way. And I think we have to be careful.
Yeah, that's a very fair point. And that could also explain why in the most recent work from this year, there is not such a clear distinction as it is here. There actually seems to populate quite well what the prediction is of the main sequence. So that is very valid, Yorick, I agree.
No problem.
Nobody died.
Hi, this is Jim Fuller. So you showed this apparent correlation between nitrogen abundance and pulsation frequency, which I was unaware of. I think that's from Connie Ertz. Is there a proposed mechanism behind that correlation?
Oh, sorry that I didn't say that. I should have said that. Is this? Oh no, this is the wrong one. Hang on. Here. So as I understand it, the idea, so folk can chime in, is that internal gravity waves can actually do some of the mixing here, and maybe they are better at doing the chemical mixing than rotation is. But I mean, I'm not sure what I think.
So why does that introduce this correlation?
That I don't know yet. Probably there is more educated people in the audience on that topic.
So this is Dominic again. So if I remembering the paper correctly, this is one of Connie's favorite papers, so please read it. She likes advertising it. I think it's very good. I don't think there is a mechanism proposed in that paper other than to demonstrate that actually pulsational mixing is something that we often neglect. And in some of these stars, it may not be rotational mixing that is the dominant form of mixing because you see that correlation. And you've also got to keep in mind for people that you'll learn about this from Mai in her review talk tomorrow, that these are acoustic modes rather than gravity modes. And that does make a big difference with any mechanism you're going to propose to explain this. The other thing that I think is included in that paper, which is important to mention, is that there's also from the analysis of this sample, which is a very homogeneously analyzed sample of B stars, because that picks up on Yorick's point about the biases that you can sometimes have, is that you get a measure of the equatorial rotation frequency from the variability of the star. And that is not a projected rotation frequency, that is the rotation frequency. And there's also not a correlation between that rotation frequency and the surface nitrogen abundance. So that addresses Vicky's comment with the projection effect as well. So from that multivariate analysis that they do, the correlations on the right are the most strong and statistically significant.
True. I did cut off the rotation frequency from this.
Sure.
Just so that it would be more easy to follow, but it's true. There is the rotation frequency. There was another panel, Falk. There was. I removed it.
You want to answer?
No.
Sorry for just yelling, and I was just asking, the way I remember it, I haven't looked at it, there was sort of a second panel to the left plot that showed those rotational frequencies, and indeed I think that's sort of even the more convincing one, because with Visan you never know. I also was quite impressed about the statistical analysis that Connie had done there, teaming up with medical statisticians. So I found that quite interesting. And to me, this is one of the papers that I look to that I think, gee, I don't want to ignore. And, my question is, what I'm trying to understand is how you align these plots, especially the second one on the left, with the notion of rotation-induced mixing and nitrogen enhancement. And you can probably come up with scenarios or multivariate scenarios that do that, but I don't know what they are. So I would like to learn more.
So you showed, Jamie Tyra. So you showed plots of magnetism, you showed plots of rotation. On the low mass side, we usually expect those to be connected. Is that true observationally for the more massive stars?
Good question. So the white dwarf, the magnetic white dwarf is spinning. So yes, it can be. The Tau score has a very, very slow rotation rate. Could be magnetic braking. Massive stars tend to have some wind mass loss that really quickly can spin down the star. I don't have a plot ready, but I think this should exist probably, Jamie. Good point.
So there's a question from Pascal about kind of these plots that we were just discussing. A simple question, is it a correlation or causation that we're seeing here? Yes, it's something about acoustic modes, but the dominating frequency of the acoustic mode is correlated with so many other aspects of the star. Is this indicating that there's some correlation there that has nothing to do with the acoustic modes themselves?
Fair point. I personally do not know if there is causation, or I would say we probably don't have that information in this sample.
Right. So I can comment, I guess, on, yeah, so that's definitely true. Dependent on what the dominant mode is, if it's a radial mode or a non-radial mode, that matters a lot, because they're probing different physics potentially. So yeah, that's a very valid point. I think in that paper as well, there's also a correlation with the amplitude of the mode as well, which is something that we don't know how to predict very well at all. So that also shows that the more dominant the pulsation, the stronger the influence it has on the stellar evolution. And I think that's a little bit more convincing than the frequency of that single mode.
Pascal says, aha. Sorry, that the correlation with the amplitude would be more interesting for wave-driven transport than a correlation with the frequency.
Any short question for the 2 minutes left? Maybe the junior scientist. I guess that includes me too, but I can make a small question. So what would be you mentioned Gaia, and I didn't see TESS in your plot. Would those be, could those influence the science on higher mass stars, or could be like later releases of Gaia or future missions like TESS, could those influence the science?
Definitely, yeah. So TESS has done wonderful things have been done with TESS data for massive stars. And this is something that I hope Maya will bring up. And also Dominic has been mentioning some few things about this. So definitely important for understanding the interior and pulsations of massive stars. Gaia has been great. So the magnetic white dwarf things were possible to identify because of Gaia distances and associating the white dwarfs to clusters to get ages of the white dwarfs. So definitely really important. I mean, for the strict stars, it would be excellent to have really good measurements of distances, because that's one of the key problems when you want to identify strict stars in the color magnitude diagram. Let me pull it up.
We're out of time, so if you have it.
So So if you want to know what is the absolute magnitude, you need to know the distance. And so to say that the star is confidently with UV excess, or it's just some main sequence massive star, you really need to know the distance. And so this is why we don't have a galactic sample yet. And also because there's a lot of extinction in the galaxy, making it harder. But with good distances, I think we could make a galactic sample, which would be really valuable for, bright stars. So this is not super bright, maybe 18th magnitude or so. And you can do many nice things in the galaxy, probably.
Thank you. Let's thank Ylva again for a great talk.